this is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to today's lecture. In this lecture, we'll discuss some problems on de-multiplexers and decoders. So that is implementation of Boolean functions using de-multiplexer and the implementation of Boolean function using decoder. So, before going into the topic, so first of all, we all know that de-multiplexer and decoder. So, de-multiplexer is a combination logic circuit whose size is given by 1 by 2 power n, where it is having one input line and 2 power n output lines, whereas n selection lines. So, based on these n selection lines, so any one of the output is selected and the input given to that particular the data available on this particular input line will be sent to that selected output line. So this is a demultiplexer. So the possible demultiplexers that we can have are 1 by 2 or 1 by 4 and 1 by 8 and 1 by 4 with from 1 by 4 we'll be using the demultiplexers. So this is demultiplexer, and the major applications of this demultiplexer is in communication. At the receiving side, we will be using this demultiplexer in order to select any one of the destination among several destinations, and the data will be sent to that. The data which is transmitted through the channel will be sent to that particular selected destination. So this is demultiplexer. And similarly, we have decoder. So what is a decoder? So decoder is also a combination logic circuit where we can have the size of decoder where the decoder performs the operation which is mainly used to convert the given binary data into decimal data, whereas encoder is converting the given decimal data into binary, which is encoding the data into some codes, whereas decoder performs the operation reverse to the encoder, where we have where this performs the conversion of binary data into decimal data. So the size of decoder is n by 2 power n, where we don't have any other inputs, only one extra control input will be there, and that control input is said to be enable input. Okay, so this is the size. So where n is the number of inputs and 2 power n is the number of outputs. So here if you look at the block diagram of this, so we'll have n input lines and one enable input. Okay, and these are n input lines, and we have 2 power n output lines. So these are the 2 power n output lines, and always the size of the decoder is represented as n by 2 power n, or else n to 2 power n decoder. So that is, we can have 2 by 4 decoder or 3 by 8 decoder, 4 by 16 and so on. So this is the decoder. So where it is used to perform the conversion of binary data into decimal data. Okay, so here for example, if you consider this 2 to 4 decoder, we have 2 inputs and 4 outputs. So based on the input combination, so any one of the output line B is enabled or it's active high, the remaining all are zeros. So this is about decoder. So this is a basic thing that we wanted to know when we are implementing the Boolean functions using decoder and demultiplexer. So now let us see the first problem. So that is f1 of ABC is equals to summation 0, 1, 4, 6, comma, f2 of A, B, C is equals to summation m of 2, 6. Using the demultiplexer, implement these functions. So implement the following functions. So let us try to explain. Implement the following Boolean function. Implement the following Boolean function. Boolean function. F1 of A, B, C is equals to summation m of 0, 1, 4, 6. and f2 of a comma b comma c is equals to summation m of 2 comma 6 using a demultiplexer. So here we have two cases. One is when when the outputs are complemented and the B is outputs are not complemented. So that means whenever we have a combination logic circuit or a sequential logic circuit, the inputs and outputs may be two types. Those are active high and active low. Active high and active low. So that is the case he has given. So what he has asked us, that is, we have to implement the above Boolean functions using demultiplexer by considering the inputs as active high ones. This is nothing but complemented means active low. This is the case when by considering the outputs as active low, and this is the case when we consider the outputs as active high. Okay, so for both the cases we have to implement the Boolean function. So for that, first of all, let me write down the truth table. So let me write down the truth table. And here both the functions are of 3 variable Boolean functions. If we have 3 input variables, so what are the possible input combinations? We can have 8 possible combinations. And let us try to write down the function output f1 of a comma b comma c, and similarly f2 of a comma b comma c. So for the given Boolean expression, first we need to write down the truth table. So what we are doing, we are drawing the truth table here. So list all the possible combinations of 3 input variables 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So these are the 8 possible combinations of input. So now based on the function f1 of a comma b comma c, so it is given that it is in the form of SOP, that is sum of products form, because this is summation m of, means these are the min terms. Min terms are also known as product terms. So that means it is a summation of product terms which are nothing but 0, 1, 4, 6. What this indicates? This indicates the min terms for which the function f1 of a comma b comma c is considered to be 1. So now what I am doing, so what are the combination for which the function output is 1? It is 0. What are the decimal equivalents here? 0, 1, 2, 3, 4, 5, 6, 7. So for the 0, it is 1. Function output, function f1 is 1, and 1 is also 1, and then 4 it is 1, and then 6 it is 1. And for the remaining, it is said to be 0. Only for the min terms m0, m1, m4 and m6, the function output, that is function f1 output, is considered to be 1. And for all the other min terms which are not present in this one, the function output is considered to be 0. Now coming to the second function, that is f2 of a comma b comma c. It is also a 3 variable function and whose output is equals to 1 for the min terms 2 and 6. So now for 2 it is 1. And 6 also it is 1, and the rest of all the combinations, the output value is 0. So this is the truth table here. Now I want to implement this one. So what is the size of demultiplexer I want to take? So as it is having 3 inputs here, so all these 3 inputs are considered to be selection inputs. So if we have 3 selection input, that is n is equals to 3, what is the size of the demultiplexer? As I told you, the size of a demultiplexer is 1 by 2 power n, that is 1 to 8 demultiplexer we require. 1 to 8 demux is required. So now I am taking the 1 to 8 demultiplexer. So here this is a 1 to 8 demux where we have only one input line. Okay, so this is my input, and we have 3 selection inputs. So let us take the 3 selection inputs as S0, S1, S2. So just assign the selection input in the order with the input variables in the same order which has taken in the truth table. So that is C, B, A. A is the MSB. So S2 is A, S1 is B, S0 is C. And we do have 8 output lines, 1, 2, 3, 4, 5, 6, 7, 8. So let us try to represent this 0, 1, 2, 3, 4, 5, 6, 7. Right? So this is a 1 to 8 demultiplexer. 1 to 8 demultiplexer. So this is a demultiplexer. Now I want to implement both the functions using the same demultiplexer. So now first up. So it is sum of products. So what are all these? These are all the minterms for which the function output is considered to be 1. So now let us identify which the function output f1 is becoming 1 for the combination 0, 1. That means when the selection input is 0, 0, 0. So the selection input is 0, 0. Then the first output line, let us consider this as y0, y1, y2, y3, y4, y5, y6, y7. So 0 will be, y0 will be selected and the input, whatever the data that is present on input will be sent to this y0. So now what I am doing, I am taking this as y0 and then y1 and y4, this is y4, okay, and then y6. So these are all given to the, these are all the product terms, okay. So these are all given to the OR gate. So this is nothing but f1 of a comma b comma c, which is equals to summation m of 0, 1, 4, 6. 0, 1, 4, 6. So this is the f1. Now let us take the f2. f2 is becoming 1 for, so let me, f2, okay, f2, and then f6. 6 is already there. So I am taking this and I am giving it to an OR gate. So this is f2 of a comma b comma c, where it is equals to summation m of 2 comma 6. Summation m of 2 comma 6. Okay, so that is how. So in this case, as the function is in the sum of products form, so we have to tie our input, logic input to, that is the input of this demultiplexer, to logic 1. So this is the case. Now let us try to identify the output of this function. So for example, if the selection inputs are 0, 0, 0, right? So that means if any one of these or inputs are 1, then the function output, any one or all are equal to 1, then the function output f1 is becoming equal to 1. So now 0, 0, 0. So already I have tied the logic input to logic 1. So this line will be selected. So this is coming here. So what is that? Logic 1, and the remaining all are set to be 0. So in that case, the function output is becoming 1. Similarly, if it is 0, 0, 1, so again this will be now 1, remaining all will be 0. So again for this also 1. So if it is 2, that is 0, 1, 0. If it is 2, so is 2 connected to first OR gate? No. So that is why all become 0, because none of the output line is selected. So that is why all are tied to 0 here, and the output will become 0. Whereas in this case, as 2 is connected to this one, as the input, that is the selection lines are 0, 1, 0. So y2 is selected and the data that is available on the input line will be sent to y2, which is equals to 1, and the remaining all the output lines will be 0, and hence the function output is said to be 1. So like that, and when it is 1, 1, 0, selection inputs are 1, 1, 0. So y6 is selected and the data available on input will be sent to y6. So y6 is now 1, as the input to this first OR gate is 1. One of the input to the first OR gate is 1. So the output will become 1. And f2 is also getting 6 as input. So the output of the second OR gate is also 1. So like that, we can implement any Boolean function, any number of Boolean functions using this demultiplexer. Okay, only the thing is just we need to identify the function, and then the minterms for which the function output is becoming 1, just tie all the inputs for which the function output is becoming 1 to an OR gate, so that the function can be implemented. So this is the case A. What is that? It is B. That is when the outputs are not complemented. When the outputs are not complemented. Now let us do the second one. When the outputs are complemented. Outputs are complemented in the sense, so we are drawing the 1 to 8 Dmax again, 1 to 8 Dmax. Okay, so where it is having 3 inputs, that is selection inputs, S0, S1, S2, which are A, B, C, and one input line. So one input line, so which is again connected to logic 1. Okay, and then here is that on outputs are complemented in the sense we need to take bubbles at the outputs. Okay, so bubble at the output or input represent, these are active low, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is 0, 1, 2, 3, 4, 5, 6, 7. So actually my function is, that is, for example, let us consider f of a comma b comma c, which is equals to summation m of 0, 1, 4, 6. Right? So what it indicates? M0 plus M1 plus M4 plus M6. What is M0? M0 means the binary combination is 0, 0, 0. M1 is 0, 0, 1. M4 1, 0, 0. 1, 1, 0. So what is the prime minterm for this one? A bar, B bar, C bar plus A bar, B bar, C plus A, B bar, C bar plus A, B, C bar. So this is the function F1. Right? So now I want to use, I want to implement this Boolean function using when the outputs are complemented. When the outputs are this is the meaning of complementation. So what I'll get here, it is bar. Bar means what is a combination? When the combination is A bar, B bar, C, so that is 0, 0, 0, then only this got selected. Right? So here what I'll get now, as the output is complemented, so I'll get A bar, B bar, C bar, whole complement I'll get. Whole complement I will get. Okay, so in order to avoid this complementation, so what I'm doing is, I'm just taking an NAND gate. Okay, so I hope you know the NAND gate operation. So 0 and this is 1. Next 4 we have. This is 4 and then 6. Then 6. Okay, so now let me check the output of this one. So what is the minterm for this one? This is A bar, B bar, C whole complement. Why I'm getting complement? Because output is having a bubble. And this one is A, B bar, C bar whole complement. And this one is A, B, C bar whole complement. Right? Now what is the answer you are going to get? A bar, B bar, C bar whole complement. This is NAND operation, right? NAND means product and whole complement. So into A bar, B bar, C whole complement into A, B bar, C bar whole complement into A, B, C bar whole complement because it is NAND. NAND means performs the AND operation and takes the complement. So here now if I expand this one, so what I'll get? A bar, B bar, C bar, complement, whole complement. This AND operation becomes plus. And then again, A bar, B bar, C, complement, whole complement. And AND operation becomes plus. A, B bar, C bar, complement, whole complement, plus A, B, C bar, complement, whole complement. So just I am expanding this complement so that AND operation becomes OR. So this complement get cancelled here. Okay. So finally what I'll get? I'll get the function as A bar, B bar, C bar plus A bar, B, C, A bar, B bar, C plus A, B bar, C bar plus A, B, C bar. So this is our F1 of A comma B comma C. I hope it is clear. So that means what I want to say, when the outputs are complemented, when the outputs are to be complemented, then just in place of OR gate, use an AND gate so that the output will remain same. So this is the implementation of the given Boolean function F1 by considering the outputs as active low, or else outputs are complemented. So similarly, I want to implement the second one. What is that? That is 2 here. So here, this is 2. Okay, I'm taking 2 and then 6. So again, I have to go for an AND gate. So F2 of A comma B comma C is equals to summation M of 2 comma 6. So this is how you can implement. So only the thing that you have to remember is when you are considering the outputs as active high, then we have to use the OR gate in order to implement SOP form of Boolean function. And if you want to consider the outputs as active low, then what should we use? In place of OR gate, we have to use the NAND gate. If it is a POS means product of sums, right? So then it will be reversed. Okay. So that is the implementation of given Boolean functions using de-multiplexer. Now let us take another one. Implement the following Boolean function summation M of 0, 1, 3, 5 using 1 to 8 demultiplexer. Here the size of the demultiplexer, it has been given. So if it is not given, we need to identify based on the number of inputs. And what is the thing that we have to do? Again, we need to draw the truth table, or else directly also you can take 1 to 8 demux here. This is 1 to 8 demux. So where we can have one input. So one input and 8 outputs we have. So the 8 outputs are 1, 2, 3, 4, 5, 6, 7, 8. Right? 0, 1, 2, 3, 4, 5, 6, 7. Right? And we have selection inputs. What are the selection inputs here? S0, S1, S2, and these are C, B, A. Right? So now, as it is again sum of products form, so we have to consider, or else we have to tie the input to logic 1. And now take the input outputs, that is 0, next 1, and then 3 and 5. So just give these to OR gate so that the function can be implemented. That's it. No need to even draw the truth table also. Directly you can connect this 0, 1, 3, 5 to this OR gate, and then you can implement the given Boolean function summation M of 0, 1, 3, 5. So if you have a POS form of Boolean function, what should we do now? So if we have a POS form of Boolean function, then you have to tie this input to logic 0, and you have to consider. So for example, I have a function F2 summation A, B, C is equals to pi m of 2 comma 6. Pi m of 2 comma 6. Right? So if it is the case, then how to implement? We just take another demultiplexer, which is a 1 to 8 demux. 1 to 8 demux here. Or else, so if it is given, then what should we do? We should get the dual of this expression. How can I get the dual of this expression? So you have to get the Boolean function in sum of products form. So what is that? How to get the sum of products form for the given POS form of Boolean function? Just writing down the minterms which are not present in the given POS form of Boolean function. So what are the minterms that are not present? Other than 2 comma 6, everything is not present in this. So we have to write that 0 comma 1 comma 3 comma 5 comma 7. Okay. Sorry, 4 is also there. Sorry. So 0 comma 1 3 4 5 7. Right? So that means the function output is 0 for these combinations. That means for all the remaining minterms, the function output is considered to be 1. So just take the demultiplexer and take an OR gate. Okay. So where the OR gate should have how many inputs? 6 inputs here. So what are the 6 inputs? 0, next 1, and then 3, and then 4, and then 5, next 7. So these are the inputs that are 0, 1, 2, 3, 4, 5, 6, 7. Right? So like that, you can, by connecting this logic input, that is the input to logic 1. So what is the thing that we have to get? We have to assign the inputs to the selection inputs, that is same as the previous case. Only the thing is, for the given POS form of Boolean function, get the SOP form of Boolean function. How to get the SOP form of Boolean function for a POS function? Just mentioning all the minterms which are not given in the POS form. So that indicates that for all these minterms, the function output is considered to be 1, because for these two minterms, the function output is considered to be 0. This is POS form. So like that also you can do it. Okay, so this is the implementation of Boolean function using De-multiplexer. Mostly you will be getting this kind of questions on De-multiplexer. Okay, he will be giving you Boolean functions, whatever it may be, the number of Boolean functions he gives. You just implement them and then use OR gates and then connect the corresponding minterms or else output lines to that OR gate, so that you can implement any Boolean function. Right? Now let us see another problem. Show that a 3 to 8 decoder and multiple input OR gate in the following expression. So that means here indirectly he has asked that we have to implement following Boolean functions using 3 to 8 decoder and OR gate. 3 to 8 decoders and OR gate. So with a single 3 to 8 decoder we have to implement it. So as you all know that 3 to 8 decoder. So what is the size? What is the number of input here? We have 3 inputs and 8 outputs. 3 to 8 decoder. So 3 inputs we have, and anyhow we'll have enable input. So this is my enable input. So the enable input may be either active high or active low. I'm taking this as active low. So then enable bar you have to take. So let us consider the inputs. How many inputs we have here? 3 inputs in the given function. So just map them as it is, A, B, C. Okay, and the outputs are, so as it is a 3 to 8 decoder, 3 inputs and 4 outputs we have, 8 outputs we have, 0, 1, 2, 3, 4, 6, 7, 8. So let us consider this as 0, 1, 2, 3, 4, 5, 6, 7. So these are the outputs, right? So now what I am doing, I just want to implement all the given Boolean functions using this 3 to 8 decoder. So first let us take the F1. So for implementing F1, so what is the function given in the form a function? It is given in the form of SOP. So SOP means, so these are all the minterms that represents, and we have to take an OR gate for each function to be implemented. So I am taking 3 OR gates here. So output of the first OR gate is F1, and second OR gate is F2, and third OR gate is F3. Right? So now I want to implement this function. So what are the inputs for which the function output is considered to be 1? 0, 4, 6. So 0. Okay. Or else, just a second. So directly I can connect 0. Right? Next 4. And then 6. So here a dot indicates that there we have a connection. There we have a connection. Whereas other output lines are not at all connected. Now coming to the F2. F2 is having only 0 and 5. So now this is the 5th input line. 0. And this one is 5. Okay. And coming to this one. Okay. Coming to this one. 1. Just a second. Or else. 1. Next. 2. 3. And 7. Right. So now I am providing the connections here. Like 1 is there, 2 is there, 3 is there, and 7 is there. right? Now let us enable input is 0 and hence the decoder is enabled. Now let us consider the output input as 0, 0, 0. So then here it indicates that what is this function? This indicates that, so if I consider this as y0, y1, y2, y3, y4, y5, y6, y7. I can write this one as y0 plus y4 plus y6. And this function I can write it as y0 plus y5. Whereas this function y0 plus y1 plus not y0, y1, y2, y3 plus y7. This is the meaning, right? So here now, if any one of the output, so what is a decoder? What is the truth table of a decoder? So decoder, for example, let us see 2 to 4 decoder, where we have two inputs, A0, B0, or else AB, where four outputs we have Y3, Y2, Y1, Y0. So if it is 0, 0, 0, 1, 1, 0, 1, 1. If it is 0, 0, then Y0 is high and the remaining all are zeros. Now 0, 1, then Y1 will be high and the remaining all are low. Then 0, 1, 0, 0. Next 1, 0, 0, 0. This is the truth table of a 2 to 4 decoder. Similarly, we can have a truth table for 3 to 8 decoder. Now, it is a case that when we can have Y0, Y0 is equals to 1. So, when the enable input is 0 because it is active low and all the inputs are 0, then Y0 is high. This one is high and the remaining all will be zeros. Remaining all will be zeros. So, this input will be 0 and hence the function output F1 is said to be 1. Whereas F2 is also 1. Okay. Next up, F3 is 0 because all these are zeros other than Y0. So, that is why F3 is 0. So, like that it decodes. Okay. So, this is the function implementation of a function using 3 to 8 decoder. Right. Now, coming to the fourth problem. Implement the following expression using 3 to 8 decoder. F of A comma B comma C 0 2 3 7, G of A comma B comma C 1 4 6 7 for active high outputs and active low outputs. So just now we have seen what is that. We have implemented a Boolean function by considering the outputs as active high and active low. Now first case, active high outputs. Active high outputs. So now what is the size of a decoder that we need to consider? We need to consider a 3 to 8 decoder. So 3 inputs and anyhow we'll have an enable input. Okay. So the 3 inputs are A, B, C. It is a 3 to 8 decoder. Okay. And now, so Y0, Y1, Y2, Y3, Y4, Y5, Y6, Y7, right? So now, first of all, F of A comma B comma C. So just take Y0, next Y2, and then Y3, okay, and finally 7. So these are given to an OR gate, right? So this is F of A comma B comma C. F of A comma B comma C. Okay. Now coming to the G of A comma B comma C. That is 1. It is 1. Okay. And then 4. 4 is there. Then 6 and 7. 6 and 7. 6 and 7. This is G of A comma B comma C. So this is the implementation of the given Boolean functions using 3 to 8 decoder with active high outputs. Now coming to the second case, that is active low. B is active low. So as we all know that active low. Okay, so here now we are taking a 3 to 8 decoder. 3 to 8 decoder. Now where this 3 to 8 decoder is having 3 inputs A, B, C and one enable input, enable, and we have 4 outputs 0, 1, 2, 3, 4, 5, 6, 7. So y0, y1, y2, y3, y4, y5, y6, y7. Right? So now I'm considering these as active high outputs. Sorry, active low outputs. If it is active low, so what I said, all the OR gates should be replaced with NAND gates. All the OR gates should be replaced with NAND gates. So now I'm taking 2 NAND gates here. So these are the 2 NAND gates. Okay. So for the first NAND gate, 0. Okay. And then 2, 3, and then 7. Now I'm taking one more NAND gate. Okay, this is f of a comma b comma c. Then to this one 1, 4, 6, 7. So 1, 4, 6, 7. 1, 4, 6, 7. This is g of a comma b comma c. So this is the implementation of given Boolean function using NAND gates and 3 to 8 decoder. This is when all the outputs are considered to be active low. So this is about the implementation using decoder. Now let us take the one more problem. Implement the full subtractor using decoder and NAND gates. The subtractor inputs are A, B, C, and the subtractor outputs are considered to be D and B naught. So first of all, let us draw the truth table for full subtractor by considering A, B, C as the inputs. Okay. And then the outputs are D and B naught. So these are the outputs of the full subtractor. Whenever you are performing the subtraction operation, there are 2 possible outputs. One is the difference and the other one is the borrow. So now I am taking the possible combination 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So this is the output. So what we are doing, we are subtracting A minus B minus C, right? So 0 minus 0, 0, 0 minus 0, 0. So difference is 0, borrow is also 0, right? So now coming to the second one. So 0 minus 0, 0, 0 minus 1. Is 0 minus 1 possible? No, we should take borrow. If I take borrow, difference also becomes 1. Now coming to 0 minus 1, again we need to take borrow. So the borrow output is 1, whereas the difference output is also 1, and 1 minus 0 is again 1. Now 0 minus 1, borrow is 1, whereas the difference is 1. 1 minus 1 again 0. Now coming to the 1 minus 0, difference is 1, and 0 minus 0, 0. So no borrow. So that is why borrow output is 1. 0. 1 minus 0, 1, and 1 minus 1, 0. No borrow, no difference. And 1 minus 1, 0, 0, 0 minus 0, 0. No borrow, and the difference is also 0. 1 minus 1, 0, 0 minus 1, borrow, and difference is also 1. So this is the output. So now I can write difference output as summation M of, for which combinations the difference output is becoming 1, that is 1, 2, 4, 7. 1, 2, 4, 7. And similarly, borrow output. B out can be given by summation M of 1, 2, 3, 7. 1, 2, 3, 7. So this is the function. This is the subtractor and its operation. Right? Now I want to implement this using how many, what is the size of decoder that I want to use? As we have 3 inputs here, 3 to 8 decoder I have to use. 3 to 8 decoder. So now I am taking a 3 to 8 decoder. So this is a 3 to 8 decoder. Okay, where we have 3 inputs. What are the 3 inputs? A, B, C, and 1 enable input. And we have 8 outputs, 3, 4, 5, 6, 7, 8. So 0, 1, 2, 3, 4, 5, 6, 7, right? So this is a 3 to 8 decoder. Now I want to implement borrow. So as he said that use NAND gates. NAND gates means whenever we use NAND gates at the outputs, we have to consider the outputs are all active low. So we are considering the outputs as active low. Now I am implementing D, that is difference function. So for 1 to 4, 7. So 1 and 2. Next is 4. Next one is 7. 1, 2, 4, 7. So this is D output. Now coming to the borrow output. Borrow output, again I have to take one more NAND gate where it is 1. It is given by 1. Next 2 is there. Just a second. 2. And then 3 also is there. 3 and then 7. So I can give these to NAND gate and the output is P out. Okay, so this is the output. So like that you can implement, or else you can implement any Boolean functions using either demultiplexer or decoder. So I hope it is clear. If it is active high inputs, if it is given to implement using AND gate, then we would have taken active high outputs. Okay, so this is the implementation. NAND gates means you have to consider the outputs are considered to be active low. Okay, if it is not mentioned, then you can implement it using OR gate. Okay, so this is the implementation of Boolean functions using decoders and the demultiplexer. So that is how we can solve the problems on implementation of Boolean functions using demultiplexers and decoders. I hope it is clear to you all. And with this procedure, you can implement any function of any number of variables, and whatever it may be the number of functions that you can implement using a single demux or single decoder. I hope it is clear to you all. If you have any doubts, you can post it in the comment section so that I can revert back. That's all for this lecture. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.